Hi students, today our topic is nucleophilic substitution reactions. Before to discuss the nucleophilic substitution, every student let's to know the what is called substitution, and after that what is called nucleophilic substitution. After that, what is the mechanism involved in the nucleophilic substitution reactions. Come to know the substitution reaction. Very simple. I am taking a molecule. In this carbon has 4 bonds. These bonds are formed with the different groups for the sake of convenience, and one of this group is replaced by another new group. The product is like this. C, here is Z, here is H, here is D, here is B, and plus A. So here the group A or atom A is replaced by the group Z or atom Z. So one group is replaced by the another group. Those reactions are called substitution reactions. Then what is called nucleophilic substitution? Very simple. If a nucleophile replaces the another nucleophile in the molecule is called nucleophilic substitution reaction. For the sake of convenience, I am taking a molecule or CH2Cl plus OH minus gives or CH2OH plus Cl minus. So here this is the nucleophile. It introduced on this carbon and the Cl is leaving from the substrate. So Cl minus is the nucleophile and the OH minus is the nucleophile. This is the attacking reagent and this is the leaving group. What is the driving force to carry this substitution reaction? OH minus strength, that means nucleophile strength, that is incoming nucleophile strength is stronger, then that is the driving force for running the nucleophilic substitution reaction. Here OH minus is the better nucleophile than the Cl minus, and other hand Cl minus is a better leaving group. So driving force for the nucleophilic substitution reaction is the attacking agent should be a better nucleophile and the releasing group is a better leaving group. Based on this is the brief explanation for the nucleophilic substitution reaction. Now we are going to discuss what are the types of substitution reactions are there. Students, what are the types of nucleophilic substitution reactions? Here on the basis of the mechanism and the factors which influence the rate of the reaction of the nucleophilic substitution reaction, here they are classified into 4 types. In this session we are going to concentrate on SN1 and SN2, and in the next session we are going to work on SNI and NGP. There are 4 types of nucleophilic substitution reactions. One is called SN2, second one is called SN1, third one is called SNI, and last one is called NGP. SN2 means bimolecular nucleophilic substitution. SN1 means unimolecular nucleophilic substitution. SNI means internal nucleophilic substitution. And NGP means neighboring group participation in the substitution reactions. Today we are going to discuss in this part SN1 and SN2. First we are going to discuss about the SN2. What is an SN2 reaction? SN2 means bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. Which nucleophilic substitutions can be categorized as SN2, or what is the mechanism involved in the SN2? Now we are going to discuss. Students, if the rate generally in the substitution reaction, one alkyl halide or one substrate is involved, one alkyl halide or substrate is involved along with the nucleophile, and which leads to the formation of products RNU plus X minus. In this reaction, rate is influenced by both the substrate and the nucleophile. Both the substrate and the nucleophile. Then that reaction can be considered as SN2 reaction. That reaction is considered as SN2 reaction. How can we say the rate, the concentration of the substrate and concentration of the nucleophile will influence the rate of reaction? Under what conditions these two will involve in the reaction? We will discuss by the mechanism, by taking the mechanism. So in the next step we are going to work out on the mechanism. Before enter into the mechanism, rate of the reaction here directly proportional to or is equal to rate constant into concentration of the alkyl halide or concentration of the substrate and parallelly on the concentration of the nucleophile. If the rate is influenced by the substrate as well as the nucleophile, those reactions are SN2 reactions, and here this reaction follows second order kinetics. Second order kinetics. Here rate law represents rate is equal to K into substrate power 1 nucleophile power 1. So sum of the powers is equal to 2. So it follows second order kinetics. Now we are going to discuss about the mechanism. Students, let's see the mechanism of the SN2 reaction. This is the schematic representation. Here nucleophile is involved, substrate is involved simultaneously in the reaction. Under what conditions the nucleophile and the substrate simultaneously involved? Where the nucleophile concentration is sufficient and where the alkyl halide is unable to produce carbocation readily, and the polar aprotic solvent is the used, polar aprotic solvents are used. Polar aprotic solvent is the solvent used in the reaction. There SN2 mechanism probability is more. Here nucleophile concentration is required and the substrate have the lower tendency to form the carbocation, and the solvent which is comfortable for this mechanism is polar aprotic solvent. So these conditions will favor the SN2 mechanism, and this nucleophile will attack this substrate. Actually X is the leaving group. Nucleophile starts to attack from backside. X is the nucleophile. X is the leaving group. So this nucleophile starts to attack from the backside. Sir, we know that point, why it attacks from the backside? That is a student doubt. During its leaving from the group, on this X atom some negative charge will develop. Nucleophile already have either negative charge or on the lone pair density that cause repulsion with this leaving group. That's why it will never attack from the front side, so it will attack from the back side. In the meanwhile, this X want to leave as a leaving group. So simultaneously this carbon will weakens its bond with the X and construct the bond with the new nucleophile. It leads to the formation of a transition state. In this transition state, carbon is pentavalent. Immediately student has a doubt. Sir, maximum valency of carbon is 4. How can you say how it is possible? Student, here carbon is pentavalent. And remember this point. Carbon is pentavalent. And second one is this molecule is planar. This molecule is planar, and this intermediate transition state have anionic character. This is a transition state. In this transition state, carbon is pentavalent. How carbon is pentavalent? Very simple, student. Here there is a sigma bond. From the knowledge of the molecular orbital theory, if this sigma bond is there, its anti-bonding sigma orbital is empty. Its anti-bonding sigma orbital is empty. That made a bond with the nucleophile. In the meanwhile, this group will eliminated, and finally you are getting this product. That's why carbon is pentavalent, and this molecule is planar, and it has an anionic character, because to the neutral species you are adding the nucleophilic group. So total charge will be negative. So this is the major point. It is the transition state. Finally, X is eliminated as leaving group, and we are getting the product. If you observe its configuration, if you observe the configuration of the reactant and configuration of the product, it is configurations are reversed. Because of nucleophile attacking from backside, configuration is reversed. So suppose it has a configuration of R, it has a configuration of S. But it is not the meaning. Before the reaction it is a dextrorotatory, after the reaction it is a levorotatory. That is wrong. Configuration only inverted. That means in SN2 mechanism, inversion takes place. Inversion takes place. That means if you are taking the R configuration structure, you may get the S configuration. Its configuration is inverted. That is called inversion takes place in this molecule, in this reaction. And whatever the configuration of the reactant, its configuration is inverted. That means the reaction is stereospecific. What is called stereospecific? Based on the configuration of the reactant, configuration of the product is decided. That is called stereospecific. Based on the configuration of the reactant, the configuration of the product is decided. That is called stereospecific. So SN2 reactions are stereospecific, and favorable is polar aprotic solvent, and there is no intermediate. Only you can see the transition state. Student have a doubt. What is the difference of intermediate and transition state? When compared with the transition state and intermediate is isolated, but a transition state never be isolated. It is a single step reaction. During this conversion, it is one state we have seen, we have imagined. Right, students? This is about the mechanism of SN2 reaction. Now we are entering into the energy profile diagram of the SN2 reaction. Students, this is the energy profile diagram for SN2. It is completed in one step. That's why you are getting only one peak. This peak, it has highest energy. That's why the highest energy, and it represents the transition state. And this is the reactant and this is the product. Why I am taking the reactant with the high energy and the product with the low energy? Generally, driving force for the reaction is formation of the stable bond. Whenever the stable bond is formed under the normal conditions, the energy of the system will decrease, so the reaction leads to the exothermic. That's why I am taking the energy of the reactant is more and energy of the product is more. This is all about SN2 reaction, but I want to recall the important points of the SN2 reactions. Number 1, SN2 reactions follows second order kinetics. And bimolecular. And second one, its rate expression is equal to K into concentration of substrate power 1 and the concentration of the nucleophile power 1. Third one, intermediate reaction completed in single step with the transition state. Transition state is pentavalent, anionic, these two are very important. And next, nucleophile attack the substrate from backside. Nucleophile attack from backside of the substrate. Backside of the substrate. And one more important point, inversion, especially it is called Walder inversion. Inversion takes place. Which type of solvent is comfortable for the reaction? Polar aprotic solvent. Polar aprotic, best example DMSO. Polar aprotic solvent is comfortable for the SN2 reaction. And which alkyl, what is the reactivity of different alkyl halides? Primary alkyl halides greater than, secondary alkyl halides greater than, tertiary alkyl halides towards alkyl halides. This is the order of reactivity. Last point, but it is important. SN2 reactions are stereospecific. SN2 reactions are stereospecific. You remember that. These are the important points for the SN2. This is the energy profile diagram. These are the important points. If you recall this information, easy to understand the mechanism. Now we are going to discuss about the SN1. Students, now we are going to discuss the SN1 mechanism. Unimolecular nucleophilic substitution reactions are simply abbreviated as SN1. In SN1 reaction, only one nucleophile is involved, only one substrate or one nucleophile is involved. Why you are calling unimolecular? Only nucleophile or only substrate involved? Or both will involve? Both are involved, but we are calling it as a unimolecular. What is the reason? Here you have used the knowledge of the kinetics. Student, here I am taking the substrate. The suitable solvent for this SN1 is polar protic. There the solvent is polar aprotic. Polar protic means it readily loses the H+. That H+ attacks the nucleophile leaving group and leads to the formation of the carbocation. That is why polar protic solvents are comfortable for the SN1 reaction. In the SN1 reaction, in the first step, carbocation is formed by the heterolytic bond cleavage between carbon and halogen. This carbocation is planar and it is a trivalent. Their transition state pentavalent, and it is not isolable, but it can be isolated. It is attacked by the nucleophile from the backside or from the front side and lead to the two types of products based on the configurations. Here students have a doubt, why this step is a slow step and this step is a first step? Student, here it involves the breaking of the bond. Here it involves the attacking of the nucleophile to the substrate. Generally, substrate is the electron deficient and nucleophile is the electron rich. electron rich species will attack the electron deficient species more comfortably. So it is a fast automatically. Here bond breaking of the bond takes the time. So that is a slow step. It is a fast step. From the knowledge of the kinetics, the slow step is the rate determining step. In the slow step, only one substrate is involved. So it is a first order kinetics. It follows the first order kinetics. But in case of SN2 reaction, two reactant and substrate both will participate simultaneously. So that is a SN2 completed in a single step. But it is SN1 completed in two steps, and the rate determined only on the concentration of the substrate. So here rate law can be written as rate is equal to K into substrate. And student, you have some observation on the attacking of the nucleophile. Here nucleophile attacks the substrate. There also it attacks. There it attacks from the back side. Here it attacks from the front side and from the back side. For the convention, here I am using some broad arrow mark. Here I am using a narrow arrow mark. Broad arrow mark represents it attacks from back side more amount and less amount from the front side. Front side attack leads to the formation of retention product, and back side attack leads to the product called inverted product. More will be attacked from the back side, so inverted product is obtained in the large quantities. More quantities is obtained. Of course, retained product is also obtained, or retention product is obtained. Both are formed if both the species, both the compounds having opposite configurations are obtained. That is called racemization. In SN1 reactions, yes, racemization takes place with more inverted product. Suppose the stability of the carbocation is more, inverted and retention product are also formed almost in the 1:1 ratio. That means 50% of the inverted product and 50% of the retained product will be formed. And one more point here. Which type of alkyl halides are comfortably participated in the SN1 reaction? Tertiary alkyl halide. Why the tertiary alkyl halide are comfortably involved in the reaction? Very simple. SN1 reaction favors with the formation of the carbocation. In another word, more stable carbocation. More stable carbocation generally given by the tertiary alkyl halide. So that's why I am taking the tertiary alkyl halide. So tertiary alkyl halides are comfortably give the more stable carbocation. Of course, benzene carbocation is more stable. So more is the stability of the carbocation, more is the rate of the reaction. More is the stability of the carbocation, more is the amount of the retention product also. Or more is the stability of the carbocation, more is the racemization. So this is the explanation for the SN1 reaction, and this is the energy profile diagram. In this energy profile diagram, if you observe, two peaks are there. In SN2, only one peak is there. Here two peaks are there, two peaks. First peak represents the transition state for the formation of the carbocation. Second peak represents the attacking of the nucleophile on the carbocation. When compared with the first peak, height of the second peak is less. That means it needs more energy. That's why this step is slow step. More is the height, more is the energy required. Less is the tendency to participate in the reaction. That's why this step is a slow step. SN1 follows first order kinetics. Rate is equal to K into substrate. This is all about the SN1 reaction. And finally, we are going to compare the SN1 and SN2 within 1 minute. Students, a brief recalling and comparison between SN2 and SN1. Main points I am right on the board. Look at this. SN2 reaction is a bimolecular completed in a single step. SN1 reaction is a unimolecular completed in two steps. Here rate directly proportional to concentration of substrate and nucleophile. There the rate is directly proportional only on the substrate. It follows second order kinetics. It follows first order kinetics. Transition state is pentavalent here with anionic character. Here no such a transition state specifically. Of course transition states are there, but the here intermediate is the carbocation and trivalent with positive charge. These reactions are stereospecific because the configuration is inverted. Whatever the configuration of the reactant, you are getting two types of products. That's why here non-stereospecific. Polar aprotic solvent is comfortable for the SN2. Polar protic solvents are comfortable. Nucleophile attacks from back side only. Here nucleophile attacks either from front side and back side. Walden inversion takes place, that means the total configuration is inverted. Here some part of the reactant undergoes inversion and some part is retained. That is called racemization. And the reactivity in SN2 reaction for the different alkyl halides is primary greater than, secondary greater than, tertiary. Here it is tertiary greater than, secondary greater than, primary. This is the differences and comparative study for the SN2 and SN1. In the next session we are going to concentrate on NGP and SNI and special conditions of the SN1 reactions. Thank you very much.